Okay, we're going to go over scalar equation of a plane. So I guess I should write that out. With a point and a normal. Okay, so this is our normal. This is the direction vector for the normal. And the normal is a line that is perpendicular to our plane. So this is our plane here. And this is a point on the plane. So we've kind of just represented it with this. And our scalar equation is usually set equal to 0. And we have ax plus by. Have you seen this version before? Yeah. Plus cz plus d. Okay. So this is our scalar version of an equation for a plane itself. And there's a couple ways we can do this. First of all, we're just going to talk about how these values, a, b, and c, are essentially the values of the normal to the plane. So there's a really quick way to do this, and we'll do that as the second method. The first method, what we're going to do is we're going to figure out a point. We're going to try to get two intersecting lines here to develop this scalar, okay? So this point here, there can be a line drawn to our normal. We just don't know what the coordinate of the point on the normal is. So what we'll do is we'll call it point P, okay? And point P will just represent with three variables because we don't know what their values are. So there's an X, there's a Y, and there's a Z to it, okay? And we can technically connect them with the line here. We'll use like a red line. There you go. So we now have two lines that are perpendicular to each other, okay? This is going to be important for us. I need to get an actual direction vector for this line here. So I'm going to subtract these 2 points, okay? So our direction vector for our, let's say, POP, so that's from our one point to the other, direction vector for this, is we're going to take our coordinates. So we have our coordinate of P, we'll say P here to start, X, Y, and Z, and our PO, and we're going to subtract them. Our point for PO was 1, 2, -3. So let's subtract the 2 to find our direction vector for this. So POP, and this will end up when we take our x coordinates. So we have x minus 1, okay, y minus 2, and z plus 3 when we subtract. Does that make sense so far? Okay, so here are our coordinates. We have variables because we don't know exactly what those coordinates are. Now, one of the things we can do is we can find the dot product between two things. So if we find the dot product between POP and our normal, well, the dot product of two things that are perpendicular is a value of 0. Okay, so because we know perpendicular lines have a dot product that's equal to 0, okay, that works out really handily for our scalar version because we have to set things into 0. We're going to find the dot product between these values, which is essentially multiplication. So we'll take our POP, our point, so we have x minus 1, oops, y minus 2, and z plus 3, the dot product of our normal. And our normal was 3, -2, and 5, right? 3, -2, and 5. So our dot product, and the dot product between the two will be equal to 0. So in this case, what we'll be doing is we'll be multiplying. So think of this kind of like distributive property. This will be 3 times x minus 1, okay, -2 times y minus 2, and positive 5 times our z plus 3 is all equal to 0. That's our dot product, the multiplication of each of those values. So when we distribute, this will become 3x minus 3 minus 2y plus 4 plus 5z plus 15 is equal to 0. Okay. Well, our x, our y, and our z, there's nothing we can do to simplify those values, right? So we have 3x minus 2y plus 5z. That's essentially our a, our b, and our c for our scalar version. And then we have -3 plus 4 plus 15. And we're going to simplify those values. This is going to give us 19, 16. I think that's what it'll give us. Yeah, positive 16. So positive 16 equals 0 with these three values. Okay. So here's our scalar version. Here's our a, our b, and our c. Now, I want to draw your attention. Maybe I have to zoom out a little to get this idea across. Our normal vector was 3, -2, and 5. Well, the a value for our scalar equation of a plane is the same as the x value of the normal. If you notice, it was the number 3. the negative 2. So the b value of the scalar equation was the same as the y value of our normal, negative 2. And 5 is the same as our z value. So though we've done it this way, we can now use a shortcut. What we can do, okay, we're going to take the original scalar. Okay, so this is, we'll call this version 2 or method 2. All right. Method 2. Okay. 0 is equal to, I guess we'll write our colors in, ax plus by plus cz plus d. Okay. No, it's already equal to 0. And remember, our normal was written as, remember off the top of my head, but luckily I can use these values, 3, negative 2, 5. Because the a, b, and c are our normal values, we can or we could have just plugged that in. So this replaces the a, our negative 2 replaces the b, and our positive 5 replaces the c. Okay, and that means 0 is equal to 3x minus 2y plus 5z plus d. Now, d is the only thing we're unknown in our method 2. So we've already done the hard part. Remember, we also had our PO, or our point, which was 1, 2, negative 3. 1, 2, negative 3. Well, those are essentially your x, y, and z value. So we're going to plug those in for the x, y, and z to isolate for d. So we get 0 is equal to 3 times 1 minus 2 times 2, right, and that was our 1, plus 5 times negative 3, plus the value of d. Well, this gives us 0 is equal to 3 minus 4, minus our 15? Yeah, minus 15 plus d. Okay, and in this case, we'll end up with negative 16 plus d is equal to 0. D is equal to the value of 16, which is exactly what we had found above. So we would just replace our d value with that, and these values are the exact same from there.